13. Okay. And probably Boris is also. Well, but maybe I can start.
Yes. Welcome, PCS members and friends, to our PCS IBS seminar. Today, we have a pleasure of hosting Professor Soumya Bera from Indian Institute of Technology in Mumbai, India. And our scientific host today is Dario, who will briefly introduce our speaker.
Yeah, thanks, Dylan. So yeah, it's a great pleasure to have Soumya today here for the talk. So Soumya studied his undergraduate studies in Calcutta University and also in IIT Madras in India. After that, he moved to Germany, to Karlsruhe, where he got his PhD in KIT of Karlsruhe, and his advisor was Ferdinand de Beers. And then he had a couple of postdoc, let's say, positions, one in Grenoble in France, and then he moved to MPI PKS in Dresden, where he's currently actually as a visitor, although after the postdoc in PKS, he moved to Mumbai as a faculty. So his research interests are, let's say, many-body quantum physics, and among them we have, for example, Cloquet systems, open quantum systems, disorder-driven quantum phase transitions, and let's say most important for us is many-body localization, and today's talk is about that, I think. Indeed, the title is Internal Clock for Many-Body Delocalization. Okay, let's welcome our speaker and let's start.
Hopefully you can hear me clearly. So thank you, Dario, for this nice introduction and also for the invitation. So today I will be talking about many-body localization, and what is the meaning of my title is delocalization. I will quickly explain. And most of the work is put up in arXiv, and this is the arXiv number. And before I start, let me thank my collaborator, Ferdinand, with whom I did this work, and it's a long-term collaboration that we have been working on this very interesting topic. Also, before I start, let me also thank my fund agencies. So this is IRCC, IITB, and also MPI PKs, with PKs we have a partner group. Good. So quickly, I will be talking about MBL very briefly. I know we do not need any introduction of MBL for currently, but very quickly I will talk about MBL thermalization and as well as certain experiments that has been going on, in particular quench experiment. And then I'll come back to today's main thing, which will be about entanglement and how to think about entanglement in this context. Okay, so let me start with the very basics. So this is what we know from the long time, that let's take a 3D Anderson insulator, and if you think about conductivity, then at temperature 0, which is this line, and if you keep on increasing disorder, at certain value of critical disorder, it will transit from metal to an insulator. So that's the conventional idea. Now, if you have temperature in your problem, immediately there will be a finite conductivity even in the insulating phase, and usually this goes under the name of variable range hopping. So that's the conventional way of thinking about temperature in the context of metal insulator transition. So for instance, variable range hopping looks following. So let's think about that. Due to the disorder, all my eigenstates are localized in different point in space. But as we know that they can live in different point in space, but can have energies that are close by. Yeah, and that's the condition that has to be satisfied actually, because if they come close in energy as well as in space, they can hybridize and localization will be destroyed. So in that sense, so they live far away but have close energy. And if you have phonon energies, then if you essentially wait sufficiently long enough, you will always find phonons energies for the particle to have gain enough energy to hop from one point in space to another point in space. So that's essentially the Mott variable range hopping, which gives you exponentially small correction to the conductivity, but even then it is finite, where this D is essentially the dimension of the problem, and delta zeta, which will come again and again in my talk, which is essentially some typical energy spacing given by one of the density of states and the correlation. Okay, so that's kind of the conventional idea, and the story of MBL kind of began because of this very pioneering work by Leiner Schuller in 2006, which says that we do not need phonon in order to conduct. So this is again the same thing. So sigma, the conductivity, is plotted as a function of temperature. And what they showed that there is a finite temperature below which there is an insulator. Yeah, so and when we talk about insulator, it is exactly in that sense that sigma of t is precisely 0. Yeah, so that's the notion of insulator, and this is why it has become very interesting, because we do not have in this particular system the notion of phonons. It's a closed quantum system, and the temperature here has to be thought about energy density. Yeah, so that's one is to replace it in order to think about what we mean by temperature here. So that's kind of the I think one of the most pioneering work in this field. Essentially, there are two sets of work. And the idea of here is that the inelastic relaxation that was given by the phonon, here it is given by electron interaction. Other way of saying that the dephasing that drives the insulator to a metal. That's more or less the picture. And since then, so this is like, let's say 20 years of now, this work started. There are plethora of work and many things have been understood, and I will not be able to give you the full overview, but let me just give you pictorially what we mean by it. Yeah. So the first slide, when I showed you metal insulator transition, it was about non-interacting system. So now we are talking about interacting system. Therefore, we need to transit from a real space to many-body Fock space. Yeah. So in the many-body Fock space, the wave functions are what we call delocalized and localized by the following thing. So let's say we think about this Hamiltonian, where the first term in the Hamiltonian takes care of the disorder itself. Yeah, so that's the non-interacting part of the Hamiltonian written in the disordered basis or in the Anderson basis. Now we have this 4 fermion interaction. So this V alpha, beta, gamma, delta are the matrix elements. In the many-body Fock space, these blue points is been represented by these Slater determinants, okay, non-interacting Slater determinants. And the connection that we see here is essentially given by this V alpha, beta, gamma, delta. Yeah, so that's roughly speaking, it's a kind of a qualitative picture of the many-body Fock space. Now, when we talk about metal insulator transition, in this language, it would imply the following, that the wave function is essentially delocalized over the many-body Fock space, whereas in the localized phase, it is kind of weakly connected to few sites and not kind of connected to all of these sites. Yeah. And that can happen given the structure of the V alpha, beta, gamma, delta. Now, the critical point, or where we see that there is a metal insulator transition in the many-body Fock space, it would imply that there is a finite connection, but essentially coming from the localized sites, the number of resonances proliferates. Yeah, and that's how the transition happens from a localized phase to a delocalized phase in the Fock space. So that's kind of the qualitative picture of this transition. And subsequently, many things have been understood. For instance, this particular transition also implies that certain thermalization hypothesis, which I will explain what it is, but eigenstate thermalization hypothesis is obeyed, as in the system do thermalize. So this is essentially the closed system version of thermalization, whereas in this particular case, when the system is localized, the thermalization is evaded. Also, at the same time, it was understood that from the entanglement perspective, if you look at a single eigenstate from the middle of the spectrum, it obeys volume law entanglement, so essentially reaching page value, and I will come back to it later. And it was also understood that in the localized phase, the entanglement scales with the area of the system. So, for instance, we will be talking mostly about one-dimensional system. There it is L to the power C, 0. Okay, so that's kind of my one slide overview of what we kind of understands about the many-body transition. Let me come back and talk about a little bit about ETH, or the eigenstate thermalization hypothesis in a closed system. So here the idea is very simple. So we start with the Hamiltonian dynamics. So that's my time evolved state. And any observable, let's say any local observable that we are interested in, one could ask what is the meaning of the local. So we are thinking about support of the operator in few sites compared to the whole system, which could be infinitely big. Now, that kind of observable written in the eigenbasis have this structure. So the first term is essentially the diagonal term, and the second term is the fluctuations, or let's say the time evolution term. Now, this OMM and ONM are the matrix elements, which is written in this way, where E and M are defined over there, which are these wave functions. Okay. So here, the idea of eigenstate thermalization hypothesis, or the fact that the system will thermalize at long time, would mean roughly the following: that this OMM is weakly depends on the energies. So you can essentially think of it as a constant term, bring it out of this summation, and it obeys, it actually averages out to microcanonical value at long time. And then this is just the normalization. Yeah? So that's the first term. The second term essentially will cancel out at very long time, because the energies will randomly, it's essentially phase. So it phases averages out. So that's, yeah.
What I don't understand is that what you call large time cannot be, a time proportional to system size, or
Yes.
Because if you have almost continuous spectrum, then certain terms will definitely survive, right?
Yes, it will survive.
So you want to take a limit when time goes to infinity before system size.
Yes, so T has to be bigger than Heisenberg time, of the order of Heisenberg time. So we need to probe the spectrum. Otherwise, it will definitely, there will be many terms which will survive.
And
so actually,
you go to this long time, but you also average over this large time.
Yes, we average over the large time, indeed. So actually, the more stricter statement is the following, that the matrix element has this following structure. So you have this diagonal term, which is the microcanonical term, and then there is so this is what we call ansatz, that there will be another term which essentially proportional to the density of states times some random number with unit variance, and a smooth function of average energy, which is E bar, and the difference in energy, which is the frequency. And these are the quantum fluctuations that do not essentially go to zero at finite system size. It fluctuates, and it goes as 1 over the volume. So that's how it decays. So the matrix elements is finite at finite system, but it goes to 0 in the infinite system size limit. Good. So that's kind of answer. There is no particular proof of this thing, but there are several numerical application, or let's say investigation, and indeed it shows that the fluctuations decays, and this local observable do attain the microcanonical ensemble result. And that's how the system thermalizes for a closed system. Good. So what I will be talking about for the next couple of slides is about these quantum fluctuations. And in particular, it turns out that one can relate the quantum fluctuations to spectral functions, which are essentially, for a spin system, could be spin correlation function or a density correlation functions. And I'll be talking a little bit about these things in a second. Okay, so before I go, so this is very generic. So this is true for any non-integrable system that we can think about, interacting non-integrable system. But for a disordered system, the situation is a little bit different, or at least what we understand, that for a disordered system, the thermalization happens through what we call avalanche mechanism. So let me give you a one slide kind of an introduction to the avalanche scenario. So here is, you think about a 1D system, 1D disordered system. And then you can imagine that due to disorder, there are fluctuations in the disorder potential. And you can have a scenario where all the spins or charge are localized in the system. However, there can be a region in space where the spins are delocalized. Yeah? So this is, I will call ergodic bubble, or a path for the system. Yeah. This is very rare. There is no doubt that this will happen only very few on very few spots, and very not very often. But also imagine the following thing, that this bubble is kind of dynamic in nature, as in that it will kind of have hybridization with the neighboring spins. Yeah, so that's just because of the interaction. So one can do a kind of a golden rule calculation. So for instance, one can say that the matrix element that connects the bubble with the rest of the localized spins decays exponentially fast because the spins are exponentially localized. So that's kind of the typical matrix elements decay. But this zeta is essentially the decay length. Now, one could argue essentially how the matrix element decays with the level spacing. So that's essentially counting. And if you look at this formula, you can show, or at least you can easily convince yourself that there is a length scale zeta for a very large n being the total size of the ergodic bubble. There could be a length scale zeta above which the decay of the matrix element will be slower compared to the level spacings. If that scenario appears, so essentially it means that the states will decay in the continuum in some way. The golden rule will be valid, and neighboring spins will become ergodic. So this is a way to thermalize the whole system, and that's what we believe that is happening, coming from the localized side for the MBL transition. Good. So, and one can essentially give an estimate of this critical length scale, which becomes 1 over the log of 2. So, but again, this is a very simple golden rule argument. People have been trying to understand this particular argument in experiments as well as in numerical experiments. And it seems there is a possibility that this mechanism wins.
Question, what defines the position of these rare bubbles?
So these rare bubbles are random in position. If that was the question.
What defines where they are? Is it the disorder, the underlying disorder realization, or is it something different?
So if I understand your question correctly, you ask where the rare bubble sits. Right. Yeah, that's random. So there is no, that is defined by the particular disorder configuration.
So if you have a disorder realization, then you basically can tell where the bubble is.
Yes.
But you said also that there's some dynamics to the bubble. So, if it is fixed by the given disorderization by its position, so it's essentially just sitting there, right? So.
Right. I understand what you're saying. So my argument is essentially based on this kind of idea that I can integrate out the high degrees of freedom. So kind of coming from the RG perspective. So when we say that the disorder fixed the bubble, but we also mean that now we have to go back and look at certain dynamical quantities. So let's say, and I will come back to it. So we can look at, let's say, density correlation functions, and we can see how that correlation evolves over time. And that kind of gives an idea of this avalanche mechanism. Okay, let me just come to experiments after this. There are several experiments by now, mostly on cold atom fold ions as well as in superconducting qubits. And I will just talk about the very preliminary experiments which has been done in the Emmanuel Bloch group. So that was essentially the first experiment. What has been shown here is essentially a situation where we do quenches. Here, it's a bit different in a sense that we have a quasi-periodic disorder compared to completely random disorder. So at a given position in space, the disorder is kind of deterministic, where the sigma is the irrational number and phi is the phase that's kind of taken arbitrarily. Now, it's a cold atomic system where it is loaded with this particular sequence of atoms. So essentially, even positions are occupied, whereas the odd positions are not occupied. So it's essentially a charge density wave. And what you measure is the response of these charge density waves over time. So essentially the pi response, not the conductivity, but the pi, Q equals to pi. And that's what we call imbalance. Okay, so what we would like to understand if the system melts or not. So if it completely melts, that's what we will call delocalization. Whereas if it remains some signature of charge density wave, then we will call it localized. Yeah, so that's kind of the yes/no answer. Okay, so that's exactly what has been plotted. So that's the imbalance as a function of time. So this delta is the strength of the disorder. It has been plotted for two different values of interaction strength. So these are Hubbard U for 1D system, and what you see that as a function of for delta 0, so no disorder, the system quickly melts and becomes ergodic or delocalized. The imbalance goes to 0. So that's the first thing. Now, at finite interaction, you can crank up the disorder strength for at least for finite time. What you clearly observe is that it decays, but then there is a finite imbalance. Particular for very large disorder, one clearly sees that there is a finite imbalance. Obviously, the experiment is not perfect. There are imperfections. There is connection to the bath, and eventually all the imbalance decays to 0. But the time scale at which it decays is much beyond this 30 time scales. This 30 is essentially in the unit of the Hawking.
Sorry,
okay, so yeah.
Should question this: the interaction U that is on-site interaction or the inter-site interaction?
So that's an on-site Hubbard. On-site, yeah. Okay. So already in this work, there is a very interesting aspect that showed up, which is the following, that what they have shown here in the y-axis is essentially these values. Yeah. So what is the long time value? So for them is the 30, and they plotted it as a function of interaction. Okay. So, and this is this red line. So at very strong interaction, you see the imbalance is very, very large. So it's very finite, whereas it goes down and comes back up as U becomes small. So there is a non-monotonic behavior already. However, there is another interesting line that dots that you see, which is what they call entanglement entropy slope. So let me just quickly mention what it is. So this is essentially assuming, so this is numerical data, not experimental data. So what they did was the following. So they simulated the problem numerically and calculated how the entanglement grows. And what they show that the entanglement is for this system size and for this time scales is kind of logarithmically growing. And that logarithmic growth has a prefactor, and that prefactor has been plotted over here.
Sorry,
yeah.
What's the value of delta over J for this plot which we discussed?
Yeah. Delta is the strength of the disorder over here.
What's the value of delta for this plot you are discussing right now?
For this value. So that's a very, yeah, sorry, I forgot what was the value of delta, but it's large.
Large, okay.
Yeah. It's not 0, because if it would have been 0, then the imbalance over here would have been 0 also.
Well, basically, I'm asking, are we in the single particle metallic regime or in the single particle localized regime?
We are in the single particle localized regime. We are in the single particle localized regime. Indeed, indeed. Great. So what I wanted to show you, or at least point out, that they are anticorrelated in a sense that when the imbalance is large, the growth of the entanglement is also slow, and that's why the slope is less. Yeah? So that's the only thing I wanted to mention from here, and that kind of a motivation for my later part of the talk. Okay, so just to quickly discuss the evolution of this experiment. So in a later year, they did a little better experiment in terms of time scale. So they indeed go from 30 to 40 now. So that's kind of the best they would do. And what they wanted to understand here is how the imbalance decay. So not only the decay to finite value or to 0, but how does it do it, especially in the ergodic phase rather than in the localized phase, because in the localized phase, you expect it to be finite. Okay, and what they show here is a log-log plot that there is a power law of decay for different values of strength of the disorder. And this has been plotted over here. So this is a function of delta, the strength of the disorder, and this exponent alpha. And what you see here that it goes below from 0.5 to somewhere finite 0.1, and that's where it stops. Okay? And that's how you get the delta C, or the critical disorder strength, where the transition happens. So now 2 points to note, one is the following, that you cannot go beyond delta equals to 2, because then in the non-interacting setting, you have a metal insulator transition in 1D for Aubrey-Andre disorder or this quasi-periodic disorder. So you want to stay above this. That's one thing. And the second thing is the following, that in a non-integrable system, you would expect that the modes are diffusive. So essentially, the charge modes will show diffusive dynamics, what would imply that essentially imply that this alpha should be around half. Yeah, so that's kind of the understanding. However, we do see much below half. So, and that's what has been dubbed as subdiffusive dynamics. Okay, what was also interesting to point out that over here, and this finiteness in the theory, in the experiment, comes because of, again, the restriction of the time scales, because there is essentially after some time the experiments cannot perform anymore. So because the time scale of decay becomes faster actually due to the Bach, so they cannot probe beyond certain time scale, and that gives a restriction on the critical disorder strength. Okay, so this is kind of the experiment. So let me come back and numerics tells us. In particular, I will talk about density-density dynamics, density-density interaction, correlation. I will tell you what do I mean by creeps, and I'll give you a little bit of what is phase diagrams. Okay, so that's going to be the main model that I'll be talking about. So this is essentially spinless Hubbard model in one dimension with density-density interaction with xx plus 1. So most of the time, the disorder will be on the density, so local potential, which is distributed between minus W to W in a random way. Dynamics will be done, so I will be mostly interested in dynamics, in particular infinite temperature. That would mean that when I will define what do I mean by infinite temperature, essentially the density matrix is identity. Okay, so in this particular model, the initial idea was that the critical disorder strength is around 3.8 when the hopping is taken to be 1 and the interaction is taken to be 1. Okay, that was kind of the initial thought. So the quantity is this fluctuations of the charge correlator. As I mentioned previously, it's a density-density correlation function to time and to space. And I will be interested in essentially the second moment of that, which is essentially the variance of this phi of xt. Now, usually the picture will be the following. So if I plot the charge correlator as a function in position space, so in a diffusive system, when you have a non-integrable diffusive system, this will be essentially a Gaussian, where the width of the Gaussian is given by this delta x and grows as t to the power half, whereas the height of the Gaussian will go down. So the return probability will go down exactly in the same way, t to the power half, minus half. Yeah, so they are related in the same way. So that's kind of the picture we would like to see in this disordered system, at least for big disorder. Yeah, so as that, okay, the model is diffusive and delocalizing. So let me show you some numerical results now. This is exactly what has been plotted here, phi x of t as a function of time at a relatively large time, and this is as a function of x. Yeah, so that's the position space. So now for a non-interacting system, we know what will happen, because in the non-interacting system, the correlation is exponentially suppressed in space. So, and that's this line that you see over here. So this line, dashed line, is a non-interacting line. Doing much below the proposed critical disorder strength, which is W1.5. And so that my system wanted to make sure that this system is indeed localized. Yeah? So the starting point is localized. Now, after time evolution, what you see here, that these are 3 different system sizes. There is no sign of this Gaussian profile that I was mentioning previously. Rather, there is this exponential feature that comes up. So the system size here is going from 16 to 24, and the time scale that we are looking at is 10 to the power 3 in terms of hopping unit. Now, this feature continues to hold for even at large disorder. So this is weak disorder 1.5. This is a bit stronger disorder 5.0, which is proposed above the critical disorder strength. And you see that almost this is independent, or at least mostly independent of system size, but there is a very different profile compared to a Gaussian diffusive profile that one would have expected for a density-density correlation. Let's analyze this. So what I plot over here, beta of t, which is essentially this delta x, how the width of this profile growing over time. So this is essentially an effective time-dependent exponent. I plotted log derivative of it as a function of the width divided by the non-interacting width. The reason for plotting it in this way is the following, that we would like to see the interaction effects, which should be beyond the non-interacting length scales. So 1 is where the non-interacting length scale ends, or where it is. So anything beyond 1 is interested in, because that's where the interaction effect is mostly prominent. So what you see here is the following, that the beta of t at weak disorder has a strong finite size effects. It's far away from half. So the number over here is essentially gives you an estimate of the exponent. And if you go from 16 to 24, and this green line is essentially 28, what you see over here, that there is no system size convergence. By that, I mean that there is no way one can expect an exponent yet. So it has yet to develop further and further to go to maybe to 5.5 or somewhere, but we do not see any growth in the, any saturation in the exponent. And that's why I draw it in this way, that in this regime, it seems the exponent is yet to converge. We can move forward, and what we see at intermediate disorder strength, that there is almost a flattening of the line, but if you closely look at it, there is also a very strong finite size effects and a tendency to go up. Eventually, at even larger disorder, the same thing persists, that if you kind of follow these curves, at even larger system size, so this system size is 32, what you see is there is a tendency to have a curvature towards left, as in is trying to saturate. And that's very small numbers, but it kind of trying to tell you that there is a very slow dynamics, even at very, very large disorder, which is beyond the critical disorder strength. Having said that, let me just propose what do we mean by kind of a phase diagram here. So this is essentially this model, this Hubbard model, spinless Hubbard, and the x-axis essentially is the strength of the disorder. So if you do not have any disorder, so that's the clean SU2 symmetric point, we do know that at this point there is a super diffusion. So we start with a super diffusion, is a KPZ scaling. I'll not talk about it for the moment, but this is what this point is. But as you move forward, we hardly see any diffusion. Rather, we see beta of t, this exponent, to be less than half, but yet to converge, whereas the slope is positive. That's what we call accelerating dynamics or transient subdiffusion. Then there is a regime which is also thermalizing, but it is a decelerating dynamics, or what we call creep, where beta t is almost close to 0, but the slope is also, how it is going to 0 is negative. So this is what has been dubbed as WC previously, which is the critical disorder strength was 3.8. But so if you look at this data, it doesn't support that critical disorder strength. Rather, it shows a broad window of regime in disorder strength where the system is thermalizing, above which we believe the true MBL takes place. However, finding that W is quite a challenge. Okay, so let me show you how the things have evolved. Let's in last couple of years. So essentially, what I call fast generation scenario, it was like 2014-7 up to 18 or so. This is one of this iconic figure by David Lewis and his group, which properties, mostly level statistics, entanglement on an eigenstate, or fluctuation of certain local observables. And this figure was supporting the fact of mobility H. So this is essentially energy density plotted as a function of disorder. And what you see that a certain disorder strength around 3.5, middle of the spectrum, there is a transition. At least that was proposed. And the critical disorder strength was between 3.1 to 8, depending on which observable you look at. Then there was the second generation kind of idea where people kept on looking at the dynamical properties, particular correlators, the one that I mentioned, imbalance, the growth of entanglement using methods like TDVP or TEBD, so DMRG techniques. The WC increased from 3.1 to 4.5 between 5.5, and the exponent, so this exponent is the correlation length exponent, or let's say localization length exponent coming from the localized phase, was told to be 1. However, we know that kind of invalidates Harris-Conan delays, so that was the idea. And finally, in last couple of years, it has developed another different type of quantities where people look at models with Bath, certain kind of resonances, also level statistics in a different way. And a different type of picture has emerged by now, which says the following, that indeed at L infinity, there is a thermal phase and an MBL phase, and this transition happens exactly where the avalanche mechanism happens. That's what I mentioned. But for finite L and for finite T, we do not see real transitions. What we see is essentially crossover physics, and different type of length scales kind of gives different numbers in these WCs. So the current estimate from this David Hughes group is essentially for this particular model where WC is greater than 20, which needs to be again checked and validated. But as of now, it's an open question. Okay, just to give you an idea, so for the 1D system, for the non-interacting 1D system, the localization are one already at disorder strength 3 or 3.5. So for WC around that number, the localization length, the non-interacting localization length is much below even the lattice spacing. So that's really, really strong disorder in that sense. So let me just conclude and show you some puzzles before I come to my next part. So I told you that there is a slow thermalization at weak disorder. Even at weak disorder, there is finite size time effects. DMRG definitely helps with system sizes, but the time that DMRG can simulate is finite. Experiments do show subdiffusion thermalization. However, one is to understand that experiment is even shorter timescales and has its own imperfections. And it turns out that the correlated versus uncorrelated disorder, by that I mean the Aubrey-Andre type of potential where you have a quasi-periodic disorder and uncorrelated is a random disorder, at least in this type of observable doesn't show any difference in terms of physics. So the puzzles are many, so I list at least 3 of these. So where is WC? Obviously is still a question for this particular model. The correlation length exponent is yet to be settled. Obviously, if in this model there is no consensus about MBL, one would ask also the question about MBL time crystals and so on. Okay, if there is no immediate question, I will go to my second part of the talk.
May I ask
yeah,
you
sure.
a stupid question? That, in which sense do you said that no consensus on is the anybody localization?
For this, as I mentioned, that there is depending on which property you look at and how you look at it, the WC, the critical disorder strength, is changing a lot. So there is no consensus on WC. So if you do not have a critical disorder strength, in that sense, I said that it's not clear, at least from our work and also from certain other works, that there is a sharp definition of WC yet. In that sense, I mean, there is no consensus.
I see. Yeah, thank you.
Yeah. Okay, so what I'm going to say in the rest of the talk is that entanglement offers an alternate viewpoint. And that may be an interesting way to look at the whole thing that I have been talking about until now. Good. So in terms of entanglement and thermalization, this is what we know. So for instance, if I define entanglement in this particular way, so essentially rho A is a density matrix of the half system. Psi is the pure state. It can be an eigenstate or a time-evolved state. And if a system thermalizes, the idea is that this entanglement goes to a thermal entropy in a finite system. Or if you do a quench in a diffusive model, it grows ballistically and saturates at the value which grows volume with the system size. Okay, so that's the page limit. In a localized system, the idea is the following: so that the systems are localized, and weakly interacting system will have overlap between this localized portion of the orbitals, which is exponentially small in systems, exponentially small in space. And if you invert this equation, one can roughly show that the entanglement grows as logarithmic of time. And that was initially an idea of entanglement. So how to distinguish these two phases dynamically. So one would expect it should grow as in a ergodic phase as proportional to t ballistically, whereas in the localized phase as a proportional to log of t. And that was very important. There were several work which actually indeed shows this logarithmic behavior. So let's the diffusion. So here is the idea of diffusion. So this is what is plotted. So entanglement as a function of time. And what you see, this is a clean system, so no disorder. What you see indeed for system size going from 16 to 26, it is indeed linear. And this thing, the saturation grows in volume. Although it is far away from page value, so it's essentially 0.7 of page value mostly. And that could be for several reasons. So one of the reasons being that I start from one particular initial state and I do not randomize the initial state. The system has conserved quantities and so on and so forth, but at least it shows volume growth. One can think about corrections. I will not go into it, but I will show you one interesting aspect of it, that the entanglement, when you scale with the time, with the entanglement infinite value, or let's say the saturation value, you see a very nice collapse of the data. And that's what we call finite size and time scaling, which clearly demonstrate that the ballistic propagation of entanglement is well supported and understood well, at least in the non-integrable models. So let me now come back and show you the localized phase. So this is the data for the localized phase, again, starting from an initial state, which is a quench initial state. And this is what has been plotted here. So this is entanglement as a function of time. At large disorders, the disorder value, as you see over here, is beyond the proposed critical disorder strength, which is 3.8. So it's supposed to be in the MBL phase. And as it plotted in the log x-axis, you expect these curves to be a straight line. So that's the proposal of the log of t. Now, I want to point out two things, that all this curve has a pronounced curvature. So they start to kind of saturate first and then they take a leftward turns. So all this curve, you see that they are going left. And if you look at the system size dependence, in particular here, or there, the larger the system size, the curvature is bigger at longer time, which kind of invalidates the fact that there is a logarithmic growth of entanglement, or one logarithmic growth being the lower bound, at least for this disorder value. So one can take this attitude again of this running exponent. So what one plot here is essentially logarithmic of entanglement with the logarithmic of time as a function of entanglement itself. And what you see here, so this is for disorder strength 4 and this is for disorder strength 6 over here. With increasing system size, what you see, there is a strong finite size effect. Not only that, we do not see a saturation, but more or less what one can show, or what one can see, that there is a possibility that this curve essentially describes a power law rather than a logarithmic. So that's kind of my first message in this work, that the entanglement itself, the proposed thing was this logarithmic growth at large disorder is kind of not clearly seen. Rather, there is an emergence of a power law even at stronger disorder, which has been missed previously.
Sorry, this system size dependence is in the new data that, I mean, let's say in the original work, probably by Polman and others, didn't see that, right?
They didn't see that because of the following reason, because their interaction strength was much smaller than the hopping strength. So the interaction was 100 times smaller, or 10, at least 100, and then 10 times smaller. So 0.01 was their interaction strength compared to the hopping. Here, the interaction strength has been cranked up to 1.
I see.
So that was, and for weak interaction, indeed, this logarithmic growth is seen, and because that was a perturbative regime, more or less.
But wait, but then let's say if you increase the interaction, then the critical disorder will be also increased. So maybe this.
No, critical disorder here is 3.8. That was if you do level spacing statistics, that's where you see the change in the curve, growing from a GOE to a Poisson statistics.
But wait, but that was seen for interaction
1
week.
No, 1.
Okay.
One. Everything is same numbers. Yeah. Right. And also the curvature, what you see here will not be there if you reduce the interaction. Eventually it will come up, but it will take longer because essentially the time scale scales with 1 over the interaction strength. So if you have a weak interaction, then the time scale that you need to simulate in order to see such a strong finite size effects is much longer.
There was any reason why they at that time they stayed with very weak interaction?
I don't know. Maybe they just wanted to see the log, and that's there. So that's probably, I don't know.
I mean, let's say at the level of how can I say, numerical techniques and so on, nothing changed with respect.
Nothing changed. Nothing changed. No. Okay. And then there was this idea that and even so let me also say the following. You can say, okay, let's forget about the short time dynamics, although this is not short because this is up to order 100, and we focus only here. And there it seems to be a straight line. Therefore, let's ignore everything else which has been shown here. And that's a bit dangerous because of the following reason. Over here is strong finite size effects. So if you want to look at, and indeed the system size with increasing system size goes left. Yeah. So you want to look at the data where the system size is converged, and there we do not see a log. That's another way of looking at the data.
I see. So essentially, the relevant time scale is determined by when the system size doesn't affect the data.
Yes. Yeah.
I see.
So one more system size, you will see even more left. And that's what has been shown over here. So one more system size, you go left.
Okay.
Good. So let me just mention, once we understand that entanglement already is showing some indication towards slow thermalization, let us again go back at the weak disorder and look at how indeed the weak disorder data look like. So this is a weak disorder 1.5. Instead of, and I'm plotting the imbalance as a function of time, as everybody would do, but I'm doing it per sample. Yeah, so these are 5-6 typical samples. There's no choice. And what you see, even at weak disorder, there's a strong variance. Yeah, so certain samples indeed go to 0 or thermalizes, but there are certain samples which is randomly chosen, is not thermalizing within the time scale that I'm looking at. This is weak disorder below W3.8, so this is W1.5. Yeah, so very weak, where we expect the system to thermalize. Now, this is a very counter view. So previously, I'm trying to localize. In the localized phase, there is a slow thermalization, but I'm coming back to weak, and I'm trying to say even at the weak, there is something to be understood already. Now, in order to reduce the fluctuation, or in order to understand these samples, these individual samples, what I'm trying to do here is the following. I'm taking the entropy as a measure of time. And this is what has been done over here. So this is imbalance as a function of entanglement for those samples, which is corresponding these samples, and ignoring ignoring can measure it in a simulation time. So this is my simulation time. This is essentially the entanglement time, if you wish. And what you see is the following thing, that for the samples which were essentially showing thermalization, indeed the entanglement is much bigger. Whereas for the sample which was essentially non-thermalizing over here, the entanglement content is much lower. Even less than half of the total entanglement that one can have in that system, which kind of gives an idea that, okay, maybe it is not a great way to look at it over time in this way, but time in the entanglement way. And it tells you that if I wait long enough for this blue line, that eventually it should go to 0 and it will reach the page value. It's just that I'm not looking at it for a small, long enough. The whole sentence can be made in a following way, that other way of saying is that the thermalization time of individual samples can be very different, and a distribution of the thermalization time is huge. That's what I wanted to say.
And will become huger and huger for large disorder, of course.
Precisely. It will become larger and larger, but there will always be that. And I will show you this plot indeed. So this is going from W1.5 to W5.0. A similar things has been shown. So few disorder sample for a relatively large sample, and you see quite a large variation. And this is the entanglement itself, proper entanglement as a function of time. And as you see that some samples essentially reach the page value, whereas some of them is still growing. Yeah, and those samples, those are still growing, are showing finite imbalance. And this is exactly what has been shown over here. So the imbalance plotted as a function of entanglement. And you see that this variation, the fluctuation has been reduced, but obviously you see that the some of them are going there, some of them. And even at larger and larger disorder, the entanglement hasn't grown much enough to show the imbalance to go to zero. And that's kind of gave us an idea of this internal clock. This is not the perfect internal clock, because clock is monotonic. Here there are oscillations and so on and so forth. So we do not think of it as an individual sample internal clock. There may be a better one. However, we found that the average internal clock is really good in the following way. So now when I say average, I mean that I am essentially averaging over many configuration of this. And this is what has been plotted here. So the imbalance itself averaged over thousands of configurations. Entanglement over here averaged over thousands of configuration for different values of disorder. I normalized it with the page value because that's essentially gives me an upper bound of 1 over here. This one should go to 0. Now I need one fitting parameter. So this is this FL of W. This one fitting parameter is required for the imbalance because as you see that overall the imbalance will decay at a given time much lower here, or close to 0 here, not that much over here. So I need to bring all of them together. So, and that's what has been done over here. What you see is that for different values of system size, all the disorder value kind of collapses on top of each other. Fitting parameter, which has been shown over here, that kind of gives an idea that essentially all of the system kind of follow this master curve. All of the disorder values follows this master curve, and eventually at longer and longer time, it will follow this top of it and kind of reach the page value, and the imbalance will go to 0. But it will happen very slowly. Yeah? So the fact is that this is a very slow process. Good. So that's my second kind of message here, that there is a different way of looking at the subdiffusion as well as the localization that I have been mentioning until now, that there is a slow thermalization, and the slow thermalization happens through this master curve for different values, different system size. Okay. So I think,
I may be confused, but maybe not. I mean, these are data that you got from various simulations and so on, but the various simulations has been evolved, all of them, irrespectively of the disorder value, for the same, let's say, time.
Yes.
Okay, so that's why, let's say, the yellow
is not yet here.
Dots, yeah, because they will need larger time. But you say,
yes.
Let's say the hint that will go
yes.
there is the fact that it's sitting on the
yes.
same curve.
Yes.
Okay.
Yes.
Okay.
Yes. Good. I think I am almost exhausted my time. So if I can get 5 more minutes, then I can probably. Okay. So this is only one observable imbalance. So if this idea works, that the entanglement can be thought of as a internal time of the system, interaction strength of the system, I should be able to do the same thing for different observable as well. And that is what I will do it very quickly, that I will now look at what is called fluctuations, time fluctuations. So that's another important quantity that should also decay if the system delocalizes. So this is 2 samples. I show you a local density, how it behaves. So you see that this blue line, so that's the interaction, non-interacting system. So you sit there and you do the quench experiment. The particle will be confined within the localization length, and within that volume, it will just do oscillations, right? So back and forth, back and forth, back and forth. That gives you this blue line. Whereas in the presence of interaction, the same sample will show this straight line, the diminishing of the interaction, diminishing of these oscillations, and this oscillation, the diminishing of these oscillations is essentially dephasing. Okay, and that's how the particle delocalizes. But still, there are samples where, for large disorder, you will see enhancement of these oscillations, and one would like to understand how this oscillation even case. Yeah, that's the time fluctuations. So which has been quantified in this way, and there is a way to understand that these fluctuations will also decay in a power law fashion, in a localized phase, whereas in the ergodic sample, it will be exponentially fast. And this is what I will show you here. So let me just focus over here. So that's the fluctuation normalized with respect to certain power. That's kind of trivial power law that one would expect. So that has been subtracted. Again, average quantity plotted as a function of entanglement for different values of disorder starting from 1.5 to 8. And what you see there is this power laws always there. And if you again allow yourself one fitting parameter over there, you see a single line. Yeah. There are two system sizes over here you do not see because the effect of system size is really small on this data, on this way of looking at the data. But what is interesting is this plot, this particular plot with one fitting parameter starting from 1.5 disorder to up to 8, which is a relatively strong disorder, you see a single master curve. And that kind of shows the similar physics that I was trying to tell previously with the imbalance, that even the time fluctuations kind of behaves in a similar manner as if they are on top of each other, following a single master curve. And eventually, if you wait long enough, everything will decay to zero. And that's kind of the slow thermalization of the creep that I was mentioning previously as well. Good. So that's kind of the another observable, which shows a similar physics for a broad range of disorder, indicating the following fact that within that disorder value, there is no transition that we could see, maybe a crossover, but no transition that we could see in this way. Okay, so let me finish over here. So I told you about the coexistence of the non-ergodic and ergodic grains or samples where there are thermalization which is happening very weakly, whereas there are other thermalization which is very fast. I talked a little bit about temporal dynamics and how it can be quantified with average entanglement flow in the system, and also the collapse that I'm trying. And in this sense, let me highlight again the phase diagram that I was trying to say, that there is a broad window of disorder strength where the system is thermalizing very slowly. And in this particular model, at least, the W star or the critical disorder strength, if it exists, has not been, I would say, found within the conventional numerics. I'll skip this plot, but I would like to thank you for your attention.
Thank you, Professor Bera, for this excellent presentation. We have time for questions.
Can you go back one slide, please, again? Just nicely. So what hinders you from going to larger disorder strength values here in this right plot?
So in this plot, the 1.5 is over here, and then if you go to 8, which is over there.
So maybe elaborating a little bit on Sergei's question. If you want to go to larger disorder, what would you need? Larger time, larger systems, both?
Both. Okay. Both. So the more the disorder strength is, you need to go to much longer time, because initially you will see that the imbalance is almost not decaying, but or at least it will decay very slowly. So what you need is a very long, very long simulations, which is not possible.
The thing that I still don't fully get is how the system size affect. I mean, I understand that you need to go to larger times. That yes, but why you need to go also to larger systems?
Oh, because it's for finite system. Eventually, there is a time scale where it saturates. So, for instance, even entanglement will saturate at exponential in L time. It will saturate to some value.
Okay.
So you want to increase that time scale as well.
I see. Okay. Okay, got it.
Yes, Alex.
Check what happens if you do a quench from a different initial state.
Yeah, that's an interesting question. So we have checked we haven't checked it carefully what happened to a different initial state, but we know from our previous experiments that if you average over initial state, things becomes a bit more difficult to disentangle, in a sense that there are other effects that comes in. When we do the trace, but there is a good reason for doing it from here. It's not the experimental reason, actually. The good reason is that these states lies very close to the middle of the spectrum in energy. So we are starting from very high energy states. It's not fully exactly at the middle, but very close. Therefore, that's one reason. And you would expect, so that's kind of the expectation, that if the energy is so high for the initial states, maybe choosing another state won't change the picture so much dramatically.
Well, yes, this was basically expectation, but this is still an assumption. So I was curious that I'm pretty much sure that another state you could consider is not like particle, no particle, particle. No
that
particle.
is a.
Yeah, that's the state you're considering, but you could, for example, just take two particles, two empty spaces, two particles, or even just run combinations.
Right.
Right. To look whether you get the same results.
Yes. No, that's important to check. We have checked at least one extra state, not fully all. The one that you mentioned, two states, and that shows exactly same, almost similar physics. Timescales are a bit different. For instance, if you start with the full half domain world state, means one domain world states where you have all up and all down, we know that the timescale is extremely large there to decay.
So it's less convenient for numerical.
It's a less convenient, exactly. It's a less convenient to start with completely one domain world state. So that's the maximally delocalized states if you wish to start with. But again, I should say that one needs to check all of these things with many more different initial states and see whether the effect survives or not. Yes.
But then actually, maybe one thing you could try is that, assuming this picture holds, for stronger disorder, you can try starting quenches from states that delocalize faster. Then you could try to compensate for. I don't have an immediate idea what would be the faster delocalizing states, perhaps. But probably there should be a way to come up with something.
I see your point. Yeah, it's a very interesting point that whether one can change the time scale with a different initial condition, and definitely it's possible.
Sorry, I thought that you say that the state that you take is the best already. No, you say is the best that you tried.
No. It need not be. So it is very close to the middle of the spectrum, but not exactly sitting on the middle of the spectrum.
Okay.
Yeah. So and that's one that we know, because actually, if you go to the clean results, the fact that it doesn't go to 1, the page value has not been exhausted, is precisely because of that the overlap of that state with the other eigenstates is not maximum here. So the density of states is Gaussian. So one has to be careful, and one has to sit exactly at the middle in order to delocalize more.
Mm-hmm.
Yeah. Sorry, getting back to this idea of engineering the initial state. Well, I wonder whether just taking a state from the middle of the spectrum of a system that is thermal, just using that.
Right. Well, if you have ideally you want to take a state which has most overlap of the eigenstates from the middle of the spectrum, because that's where the most entanglement quantity is. Because that if you even look at the entanglement of eigenstate, it has this parabolic type of this kind of behavior. It's not that all eigenstates are maximally page, right? So actually the best system to look at these kind of things, just to tell you, is the Floquet system, because there the eigenstate does not have any structure. So the density of states is flat. And there you can choose any state and it should work. And actually, I have simulations where it does work in that settings.
Oh, right. That actually brings naturally a question. So did you try the same? Did you try to check the same thing for the Floquet systems?
Yeah, it works. It works. It nicely works. We are in the process of finishing it. Yeah.
Okay. Do we have any further questions? Seems not. So in this case, let us thank our speaker again.
Okay, thank you. Thank you very much.